Hi, my name is Michael Haider. I'm a postdoctoral researcher at the Computational Photonics Group at Technical University of Munich. Today, I'm going to present on project skeletons for scientific software, especially on the Berta project, which is a C++ skeleton with a Python interface. Here you can see my co-authors, Michael Riesch and Christian Jiroszek, and we are all with the Department of Electrical and Computer Engineering of Technical University of Munich. In the following, I'll give you a brief introduction and then talk about best practices in software engineering. We'll review existing project skeletons in the scope of scientific computing. I'll present you our own implementation of Berta, which is, as I said, a C++ skeleton with a Python interface, and then we'll draw some conclusions. So what is the scope and the aim of all this that I'm going to present you here? As you know, research, especially in scientific computing, relies heavily on the use of software packages such as mathematical libraries or data analysis tools. However, it is quite hard to get funding to develop and maintain such packages. What gives us as software engineers in scientific computing valuable information on how to implement good scientific software are development guidelines and best practice guides. For new projects, however, the implementation of these best practices in software engineering must always be carried out from scratch. So if you do a new project, you always have to make sure that all the best practices are implemented. This task, however, can be automized in terms of ready-to-use project skeletons. And this makes it possible for us scientists to focus on the actual implementation, which is typically a formidable challenge on its own. So let's review some of the best practices in software engineering. So what is always suggested in software engineering is to do some kind of project management. This means the use of a version control system and a project management tool. What is also important is to stick to a predefined workflow. So a workflow that manages how you use your version control system, how you make changes to the code. The code itself should have some predefined style. So one should agree on code formatting before the actual implementation of the software. This can be done automatically, and the code can be checked whether it complies to some code style or code format. What is also important is static, in this sense, a static code analysis. So some linter should be there to analyze the code during at compile time, basically. Another important part is independence. So you don't want your scientific code to depend on some third parties. So it is recommended to use open file formats and open source libraries. Some of the tasks, such as build and testing, can be automized. Therefore, we suggest to use build automation systems that ideally run in continuous integration pipelines. One part in software engineering that I cannot stress enough is extremely important is documentation. And the documentation includes first of all, a big picture documentation that basically summarizes the scope and how to use a certain software project, and an in-depth, detailed function reference on what each module and each function in the software does. In order to produce good quality software, testing is also very important. This means we should write code and functions in such a way that one function serves one purpose, and we should test the functions according to this purpose in terms of unit tests. So the use of a unit test framework is highly recommended. And in order to see what part of the code is really tested and how much a test covers of the code, a code coverage report should be generated. The last part in the best practices in software engineering is the deployment, which is typically kind of neglected for scientific computing projects. And this is the part where we really package our binaries and document how a user should use the scientific software package, in order to get some results here. So deployment is also an important part in the end, because this really makes a difference in if the code is used, if a project is supported or not. So in this sense, let us now review some of the existing project skeletons for scientific software. For this, we consider three different types of exemplary projects. First of all, a C++ project, which serves as an example for a compiled programming language. Then we consider a Python project, which is an interpreted language. And as a third project, we consider a LaTeX project, which represents miscellaneous software. A C++ project has a very complex compilation and linking process, depending on external libraries and whatsoever. So therefore, a quite intricate project skeleton is required if one builds C++ projects. Because C++ is now around for several years and it's a very common programming and highly performant programming language, there are several approaches available that set up project skeletons for us to use. Also, Python gained a lot of momentum in recent years, so there are also there's a helpful skeleton available in Python. Python does not have this complicated compilation and linking process because it's an interpreted language, so the overall structure of the project skeleton is a bit simpler here. Finally, for LaTeX projects, we could not find any skeleton that is available up to now. And yeah, we'll come to this later on. And let's see how different projects implemented best practices, and if there was no implementation of this certain best practice that we discussed before, we added our own suggestions, and our own suggestions are marked with an asterisk here. So like with this asterisk here. So for LaTeX, we didn't find any. So basically all the best practice implementations that you see here are our suggestions. So for the version control system, basically all of the best practices that are now all of the implementations for project skeletons that we found. So for C++, we have this project here. For Python, we have this project, both hosted on GitHub. And they all use Git as a version control system, which is the quasi-standard for in software development today. For collaboration platforms, we have GitLab and GitHub available. And also for the workflows, there's the GitLab flow and the GitHub flow. They're quite similar. I think GitLab flow is a bit stripped down, a bit simpler than the GitHub flow. So based on a little less branches. But in the end, one just should stick with one workflow and yeah, go ahead with this. For code formatting, we have CLang format for C++, black for Python, and there's LaTeX indent that creates indentation for and beautifies the LaTeX code. Static code analysis, so linting, there's PyLint for Python, LaCheck for LaTeX, and CLang tidy for doing static code analysis in C++ code. Then, as said before, the use of open file formats is highly encouraged, and also the use of open source libraries. So here we just name a few, like FFTW for fast Fourier transform, a quick fast Fourier transform implementation, and the GNU Scientific Library. And depending now on which platform you use, you have the option for GitLab CI, which is the continuous integration implementation in GitLab, or for GitHub, there is Travis CI, which is a continuous integration of a third party that works with GitHub. For build automation, we suggest the use of CMake for C++ as well as for LaTeX. In Python, there is no build process because it's an interpreted language, so there is no build automation required here. Then you see the function reference here, Doxygen, Sphinx, Docstrip, documentation, markdown, restructured text, and LaTeX itself. So it's quite common to use LaTeX to write the documentation for LaTeX modules. So this refers to the big picture documentation here. Then it's also important to do unit tests. So there's catch2 PyTest, code coverage reports using gcoff or coverage.py. And then finally we have the deployment, and here we suggest for C++ to use Conda, which is a general package repository. For Python, the standard is PyPI, so it's a Python package index. And for LaTeX, the standard way of distributing LaTeX packages is C10 here. Okay, and then for online documentations, there are GitLab pages and GitHub pages available to push the actual documentations for the end user. Okay, now let's present Berta, which is a project skeleton for C++ code with a Python interface. This combination of highly performant C++ code with a flexible Python interface is quite common in scientific computing. Then there are basically two ways to realize such a combination. The first way is to annotate Python code to create a C or C++ extension, for example, using Python. Or the other way around is basically to automatically create a Python interface from a C++ library. This can be done, for example, using the Swig project. In recent work, we used the Swig project to create Python bindings for a C++ library, and we found that the required build steps in order to do so are quite complex. Then we were looking for a readily available project skeleton, and we did not find any that includes both C++ library with a Python interface. And so we created Berta, which is open source and can handle and combine these two different programming languages with a highly performant compiled language and a interpreted scripting language like Python. It is important to stress that Berta implements all the key elements regarding the best practices in software engineering. And for this, we chose the respective candidates for a C++ project that were listed before in this table here. So Berta implements all these suggestions. So in addition to reference 4 here, we also have a code coverage report using GCOV, and we have deployment using Conda here, which would make Berta alone, for C++ projects alone, the most comprehensive project skeleton available. Additionally, the required steps to build and install a Python interface module have also been implemented. And the deployment of the project overall is enabled with the help of a Conda feedstock. Here you see the overview on how a project in Berta is built and created. So here you have your source code, your unit test framework hosted on some GitLab, for example. Then you have the build step, which is automated using CMake, creating Swig, and using Swig a Python module, shared libraries. You can run unit tests and create a code coverage report. Documentation is also automatically built. And then in another continuous integration pipeline, we have a CLang format that checks if the code complies to our coding style. So we have quality testing and deployment in, because the ready-made modules can be deployed on Conda Forge, and you can directly download these things, and the documentation is then pushed to GitLab pages. If you want to use Berta for your own projects, you can just go to the GitHub page, github.com/cphtomberta, and just click use this template. You can also create your own project using the new project button here, and you can directly reference the Berta project for the repository in the repository template here. So we used the Berta projects ourselves in scientific computing, for example, to create a software project for the simulation of rapidly tunable 3-domain mode-locked fiber lasers. And this project requires several third-party libraries, for example, scientific libraries such as FFTW, GNU Scientific Library, and so on, and also libraries for storing the output data. In this case, it was HDF5. And all these dependencies are conveniently installed using Conda, and they are all then detected by the CMake build automation system. Another important use case for the Berta skeleton is MBSolve, which is an open source solver for the Maxwell-Bloch equations. But in this case, the actual project was there before the project skeleton, and we used this MBSolve project as a reference for implementing all these best practices. So that basically already concludes our talk. So what have we done? We have reviewed the state-of-the-art in Project Skeleton that facilitate the implementation of good software engineering practices in scientific software projects. And for this, we proposed a new skeleton for a C++ library with Python bindings in terms of our Berta project. However, there are no skeletons available for LaTeX projects, but we think that such a skeleton would facilitate the collaboration between researchers in the scope of scientific publications, and therefore we propose to provide such a skeleton for LaTeX in the scope of future work.